Hi everyone, I am Swapna Davis of ECE Department, Rajagiri School of Engineering and Technology. I am going to introduce you to the cellular concept. You can see the basic cellular system. Every hexagon is representing a cell, and at the center of every cell there is a base station. All the base stations are connected to the mobile switching center, which is further connected to the public switch telephone network. As we have seen, a single high-power transmitter is replaced by many low-power transmitters. Every base station is allocated a group of channels. Neighboring base stations are assigned different groups of channels to minimize the interference. By limiting the coverage within a cell, that is, the transmitted signal power from a base station will be good enough only within a cell, the same group of channels can be used in different cells separated by large distances. This figure is showing the basic idea of a frequency reusing in cellular technology. Cells with the same letter use the same group of channels. You can see the cells labeled as A, B, C, D, E, F, G, and you can see three such groups. Every group is called as a cluster. The hexagonal cell shape is conceptual and it allows the easy analysis of the cellular system. The actual radio coverage of a cell is known as the footprint and it can be decided from the radio field strength measurements. If you are going for the circular shape, adjacent circles cannot be overlaid upon a map without gaps or overlapping regions. Without overlapping, there are three choices available to us: a square, an equilateral triangle, and a hexagon. A cell must serve the weakest mobiles located at the edges of the cell. For a given distance between the center of the polygon and its farthest perimeter points, the hexagon has the largest area of the three. Using the hexagon geometry, a minimum number of cells can cover a large geographic region. Hexagon approximates a circular radiation pattern for an omnidirectional base station antenna. For center excited cells, base station transmitters are at the center of the cell, and for edge excited cells, base station transmitters are on 3 of the 6 cell vertices. Omnidirectional antennas are used for center excited cells and sectored directional antennas are used in corner excited cells. Consider a cellular system with a total of S duplex channels. If every cell is allocated a group of K channels and if the S channels are divided among N cells, then the total number of available channels can be given by S equal to Kn. The N cells, which use the complete set of available frequencies, is called as a cluster. In the previous figure, there were three clusters. If a cluster is replicated m times in the system, the total number of channels, C, which is a measure of the capacity, is given by C equal to mkn, which is further equal to ms. The capacity is directly proportional to the number of times a cluster is replicated. The factor n is called as the cluster size and its values are typically 4, 7 or 12. If the cluster size n is reduced while the cell size is kept constant, more clusters are required to cover a given area and hence more capacity is achieved. A large cluster size indicates that the ratio between the cell radius and the distance between co-channel cells is large. A small cluster size indicates that co-channel cells are located very close together. The value for n is a function of how much interference a mobile or base station can tolerate to maintain a certain quality. A smallest possible value of n is desirable to maximize the capacity. The frequency reuse factor of a cellular system is given by 1 by n, since every cell within a cluster is only assigned 1 by n of the total available channels in the system. And this is showing the location of the co-channel cells. The cells labeled A are adjacent co-channel cells. That is, these are the cells using the same set of channels. The geometry of the hexagon is such that the number of cells per cluster n can take the values satisfying the equation n equal to I square plus ij plus j square, where I and j are non-negative integers. To find the nearest cochannel neighbors of a particular cell, move I cells along any chain of hexagons and then turn 60 degrees counterclockwise and move j cells. In the figure, I equal to 3 and j equal to 2 and n equal to 19, which you can verify. Next, we can see the channel assignment. The strategies are classified into fixed or dynamic. In a fixed channel assignment strategy, every cell is allocated a predetermined set of channels. Any call attempt within the cell can only be served by the unused channels in that cell. If all the channels in that cell are occupied, the call is blocked and the subscriber does not receive any service. Several variations of the scheme exist. In one approach, called as the borrowing strategy, a cell is allowed to borrow channels from a neighboring cell if all of its channels are already occupied. In a dynamic channel assignment, voice channels are not allocated to cells permanently. Every time a call request is made, the serving base station requests a channel from the MSC. MSC allocates a channel to the requested cell following an algorithm. MSC allocates a channel if it is not presently in use in the cell or any other neighboring cell to avoid the interference. Dynamic channel assignment reduces the probability of blocking, which increases the trunking capacity of the system since all the available channels are accessible to all of the cells. Dynamic channel assignment strategies require the MSC to collect real-time data on channel occupancy, traffic distribution, and radio signal strength indications of all the channels on a continuous basis. This increases the storage and computational load on the system but provides increased channel utilization and decreased probability of a blocked call. Next, we will see the handoff. When a mobile moves into a different cell while a conversation is in progress, the MSC transfers the call to a new channel in the new base station. An optimum signal level at which the handoff to be initiated will be specified. A particular signal level is specified as the minimum usable signal for an acceptable voice quality, and this is in between generally minus 90 dBm to minus 100 dBm. A slightly stronger signal level is used as a threshold at which a handoff is made. The margin delta is defined as a peer handoff minus peer minimum usable, and this cannot be too large or too small. If delta is too large, unnecessary handoffs will be taking place, which will be burdening the MSC. If delta is too small, then there will be insufficient time to complete a handoff before a call is lost due to weak signal conditions. The handoff scenario at the cell boundary is shown. You can see that a vehicle is moving from cell 1 to cell 2. First one is showing the improper handoff situation and the second one proper handoff situation. The signal strengths at location A in cell 1 and location B in cell 2 are shown in both the cases. In the first case, the handoff is not completed properly, so when the vehicle reaches the point B, the call is lost. And in the second case, the handoff is done correctly, and when the vehicle reaches the point B, again we have good signal strength. Call dropping can happen when there is an excessive delay by the MSC in assigning a handoff or when the threshold delta is too small. Excessive delays will be occurring because of high traffic conditions. We have to ensure that the drop in the signal level is not due to momentary fading and the mobile is really moving away from the serving base station. For this, the base station monitors the signal level for a certain period of time before a handoff is initiated. The time over which a call is maintained within a cell without handoff is called as the dwell time. In first generation systems, signals like the measurements are made by the base stations and supervised by the MSc. In the second generation systems, handoff decisions are mobile assisted. In mobile assisted handoff, every mobile station measures the received power from surrounding base stations and continuously reports to the serving base station. A handoff is initiated when the power received from the base station of a neighboring cell exceeds the power received from the current base station by a certain level or for a certain period of time. The Maho is much faster since the handoff measurements are made by each mobile and the MSc no longer constantly monitors signal strength. During the course of a call, if a mobile moves from one cellular system to a different cellular system controlled by a different MSc, an intersystem handoff becomes necessary. Prioritizing handoffs. One method for giving priority to handoff is called the guard channel concept. A fraction of the total available channels in a cell is reserved exclusively for handoff requests. This method has the disadvantage of reducing the total traffic. Queuing of handoff requests is another method to decrease the probability of a forced termination. There is a trade-off between the decrease in probability of a forced termination and total carried traffic. Next is the practical handoff considerations. In practical cellular systems, several problems arise in design for a wide range of mobile velocities. High-speed vehicles pass through the coverage region of a cell within seconds, whereas pedestrian users may never need a handoff during a call. MSc gets burdened if high-speed users are constantly passed between very small cells. Another practical limitation is the ability to obtain new cell sites. Additional channels and base stations at the same physical location of an existing cell are provided, rather than finding new site locations. By using different antenna heights and power levels, it is possible to provide large and small cells which are co-located at a single location. This technique is called as the umbrella cell approach. This provides a large area coverage to high-speed users while providing small area coverage to the users with low speeds. The umbrella cell approach is shown here. Large umbrella cell for the high-speed traffic and small microcells for the low-speed traffic. The umbrella cell approach ensures that the number of handoffs is minimized for high-speed users and provides additional microcell channels for pedestrian users. Another practical handoff problem in microcell systems is known as cell dragging. This results from pedestrian users that provide a very strong signal to the base station. This occurs in an urban environment when there is a line of sight radio path between the subscriber and the base station. As the user moves away from the base station at a very low speed, the average signal strength does not decay rapidly. Even when the user has traveled into the neighboring cell, the received signal at the base station may be above the handoff threshold, thus a handoff may not be made. This creates a potential interference and traffic management problem. In channelized wireless systems, different radio channels assigned during a handoff called as a hard handoff. Spread spectrum mobiles share the same channel in every cell. Handoff does not mean a physical change in the channel, but rather a different base station handles the radio communication. By simultaneously evaluating the received signals from a subscriber at several neighboring base stations, the MSc may actually decide which version of the user signal is the best. MSc makes a soft decision that which version of the user signal to pass along to the PSTN at any instant. The ability to select between the instantaneous received signals from a variety of base stations is called soft handoff. Next is interference and system capacity. Interference is the major limiting factor in the performance of cellular radio systems. Sources of interference are another mobile in the same cell, a call in progress in a neighboring cell, other base stations operating in the same frequency band, or any non-cellular system leaking energy into the cellular band. Interference on voice channels causes crosstalk. On control channels, interference leads to missed and blocked calls due to errors in the digital signaling. Interference is more severe in urban areas. Interference is the major bottleneck in increasing the capacity. The two major types of system-generated cellular interference are co-channel interference and adjacent channel interference. Co-channel interference and system capacity. In a given coverage area, there are several cells using the same set of frequencies. These cells are called as the co-channel cells, and the interference between signals from these cells is called as the co-channel interference. Consider thermal noise, which can be overcome by increasing the signal-to-noise ratio. Co-channel interference cannot be overcome by simply increasing the carrier power of a transmitter. It increases the interference to neighboring co-channel cells. To reduce co-channel interference, co-channel cells must be physically separated by a minimum distance. When the size of every cell is the same and the base stations transmit the same power, the co-channel interference ratio is independent of the transmitted power. It is a function of the radius of the cell and the distance between the centers of the nearest co-channel cells. By increasing the ratio of D by R, the separation between co-channel cells is increased and interference is reduced. The co-channel reuse ratio Q is related to the cluster size. For a hexagon geometry, Q equal to D by R, which is equal to root 3n. Smaller n, greater is the capacity. Co-channel reuse ratio Q are given for some values of n. A small value of Q provides a larger capacity and a large value of Q improves the transmission quality. There is a trade-off between the two. Let I0 be the number of co-channel interfering cells. Then the signal to interference ratio for a mobile station which monitors a forward channel can be given by S by I equal to S by summation I equal to 1 to I0 II. S is the signal power from the desired base station. II is the interference power caused by the ith interfering co-channel cell base station. The average received signal strength at any point decays as a power of the distance between a transmitter and receiver. The average received power PR at a distance d from the transmitting antenna is PR equal to P0 times d on d0 to the power of minus n, or PR in dBm is equal to P0 dBm minus 10n log d on d0. P0 is the power received at the reference point in the far field region at a small distance d0 from the transmitting antenna. N is the path loss exponent, which is 2 to 4 generally. If di is the distance of the ith interferer from the mobile, the received power due to the ith interfering cell will be proportional to di to the power of minus n. When the transmit power of every base station is equal and the path loss exponent n is the same throughout the coverage area, the S by I ratio for a mobile can be given by S by I equal to R to the power of minus n division summation I equal to 1 to I0 di to the power of minus n. Consider only the first layer of interfering cells. If all the interfering base stations are equidistant from the desired base station, and if this distance is equal to d between cell centers, then S by I ratio is given by d by R to the power of n division I0, and this is equal to root 3n to the power of n division I0. This relates S by I to the cluster size n, which in turn determines the overall capacity of the system. This figure is showing a 7-cell cluster system. The distances from a mobile station at the center cell to the various co-channel interfering cells are shown. For a 7-cell cluster with the mobile unit at the cell boundary, the mobile is at a distance d minus r from the two nearest co-channel interfering cells and approximately D and D plus R from other interfering cells in the first tier. For n equal to 4, the signal to interference ratio for the worst case can be given by S by I equal to R to the power of minus 4 division 2 D minus R to the power of minus 4 plus 2 D plus R to the power of minus 4 plus 2 D raised to minus 4, or S by I equal to 1 division 2Q minus 1 to the power of minus 4 plus 2Q plus 1 to the power of minus 4 plus 2Q to the power of minus 4, when Q equal to D by R is replaced in the equation. For n equal to 7, the co-channel reuse ratio Q is 4.6 and the worst case S by I is 17.8 dB. Hence, for a 7-cell cluster, the S by I ratio is slightly less than 18 dB for the worst case. To improve performance in the worst case, it would be necessary to increase n to the next largest size, which is 12. This decreases the capacity since 12-cell reuse offers a spectrum utilization of 1 by 12 within each cell, whereas 7-cell reuse offers a spectrum utilization of 1 by 7. In practice, a capacity reduction of 7 by 12 cannot be tolerable to accommodate for the worst case situation. Next is adjacent channel interference. Interference resulting from signals adjacent in frequency to the desired signal is called as adjacent channel interference. Adjacent channel interference results from imperfect receiver filters which allow nearby frequencies to leak into the passband. The problem can be serious if an adjacent channel user is transmitting very close to the subscriber's receiver while it receives a base station signal. This is referred to as the near-far effect, where a nearby transmitter captures the receiver of the subscriber. Alternatively, the near-far effect occurs when a mobile close to a base station transmits on a channel adjacent to the one used by a weak mobile. The base station may have difficulty in discriminating the desired mobile user because of the close adjacent channel mobile. Adjacent channel interference can be minimized through proper filtering and channel assignments. Since every cell is given only a fraction of the available channels, a cell need not be assigned channels which are all adjacent in frequency. By keeping the frequency separation maximum between each channel in a given cell, the adjacent channel interference can be reduced considerably. By sequentially assigning successive channels to different cells, we can achieve separation of n channel bandwidth, where n is the cluster size. Some channel allocation schemes avoid the use of adjacent channels in neighboring cell sites. For small n, the channel separation may not be sufficient to keep the adjacent channel interference level within tolerable limits. Example, if a mobile is 20 times as close to the base station as another mobile using adjacent channel, the signal to interference ratio for the weak mobile is around S by I equal to 20 to the power of minus n. For a path loss exponent n equal to 4, this is equal to minus 52 dB. Power control for reducing interference. In practical cellular systems, the power levels transmitted by every subscriber unit are under constant control by the serving base stations. This is done to ensure that every mobile transmits the smallest power necessary to maintain a good quality link on the reverse channel. Power control not only helps prolong battery life for the subscriber unit, but also reduces the reverse channel S by I in the system. Next, we will see the trunking and grade of service. Cellular systems rely on trunking to accommodate a large number of users in a limited radio spectrum. Trunking allows a large number of users to share a small number of channels in a cell by providing access to every user on demand from a pool of available channels. In a trunk radio system, every user is allocated a channel on demand, and upon termination of the call, the channel is immediately returned to the pool of available channels. Trunking exploits the statistical behavior of users. The telephone company uses trunking theory to determine the number of telephone circuits needed to meet the user demand. The same principle is used in designing cellular radio systems. In a trunk system, when a particular user requests service and all the radio channels are already in use, the user is blocked. In some systems, A queue may be used to hold the requesting users until a channel becomes available. The measure of traffic intensity is Erlang. One Erlang represents the amount of traffic intensity carried by a channel that is completely occupied. Example, a channel that is occupied for 30 minutes during an hour carries 0.5 Erlangs of traffic. The grade of service is a measure of the ability of a user to access a trunk system during busiest hour. The busy hours occurs between 4 p.m. and 6 p.m. on a Thursday or Friday evening. GOS is typically given as the probability that a call is blocked or the likelihood of a call experiencing a delay greater than a certain queuing time. Setup time is defined as the time required to allocate a trunk channel to a requesting user. Blocked call is the call which cannot be completed at time of request due to congestion. Holding time H is the average duration of a typical call. Traffic intensity A is a measure of the channel time utilization, which is the average channel occupancy measured in Erlangs. Load is the traffic intensity across the entire trunk radio system measured in Erlangs. Grade of service is a measure of the congestion specified as the probability of a call being blocked, which is the Erlang B case, or the probability of a call being delayed beyond a certain amount of time is Erlang C case. Request rate is the average number of call requests per unit time, denoted as the lambda per second. The traffic intensity offered by each user is AU equal to lambda H. For a system containing U users and an unspecified number of channels, the total offered traffic intensity A is given as A equal to UAU. If there are C channels in a trunk system and the traffic is equally distributed among the channels, then the traffic intensity per channel AC is AC equal to UAU division C. There are two types of trunk systems. First type, when a user requests service, immediate access to a channel is given if available and no queuing. If no channels are available, the user is blocked and is free to try again later. This type of trunking is called block calls cleared and assumes calls arrive as a Poisson distribution. Consider there are infinite number of users and all users including blocked users may request a channel at any time. The probability of a user occupying a channel is exponentially distributed, that is longer calls are less likely, like an exponential function. There are a finite number of channels available in the trunking pool. This is known as an MMQ. Erlang B formula, that is a block to calls cleared formula, determines the probability that a call is blocked and is a measure of the GOS. Erlang B formula is given by probability of blocking equal to a raised to c on c factorial division summation k equal to 0 to c a raised to k on k factorial, and this is the grade of service, where C is the number of channels in a trunk system and A is the total offered traffic. Second type provides a queue to all calls which are blocked. If a channel is not available immediately, the call request can be delayed until a channel becomes available. This type of trunking is called blocked calls delayed. Its measure of GOS is the probability that a call is blocked after waiting a certain length of time. The likelihood of a call which is delayed is given by Erlang C formula, that is probability of delay greater than 0 equal to a to the power of c division a to the power of c plus c factorial 1 minus a by c summation k equal to 0 to c minus 1 a raised to k division k factorial. If no channels are immediately available, the call is delayed. Probability that a call is delayed greater than t seconds is equal to the probability that a call is delayed multiplied by the conditional probability that the delay is greater than t seconds. The GOS of a trunk system where blocked calls are delayed is hence given by probability of delay greater than t is equal to probability of delay greater than 0 multiplied by probability of delay greater than t conditioned on delay greater than 0, and this is equal to probability of delay greater than 0 multiplied by exponential minus t c minus a division h. The average delay d average is equal to probability of delay greater than 0 multiplied by h on c minus a. Trunking efficiency is a measure of the number of uses offered with a particular GOS with a fixed channels. Improving coverage and capacity. As the demand increases, the number of channels assigned to a cell becomes insufficient. Techniques such as cell splitting, sectoring, and coverage zone approaches are used to expand the capacity of cellular systems. Sectoring uses directional antennas to control the interference and frequency reuse of channels. The zone microcell concept distributes the coverage of a cell and extends the coverage to hard-to-reach places. Cell splitting increases the number of base stations to increase capacity. Sectoring and microcells rely on base station antenna placements to improve capacity by reducing the co-channel interference. Cell splitting and microcell techniques do not suffer the trunking inefficiencies experienced by sectored cells. It enables the base station to oversee all handoff codes related to the microcells, thus reduces the computational load at the MSC. Cell splitting. A congested cell is subdivided into smaller cells, each with its own base station and a reduction in antenna height and transmitter power. Cell splitting increases the capacity of a cellular system since it increases the number of times the channels are used. By defining smaller cells between the existing cells, capacity increases due to the additional number of channels per unit area. If the radius of every cell is reduced to half to cover the entire surface area, the number of cells required will be 4 times. Example, consider a circle with radius r. The area covered by such a circle is 4 times large compared to a circle with radius r by 2. The increased number of cells would increase the number of clusters and thus capacity. Cell splitting maintains the minimum co-channel reuse ratio Q between co-channel cells. This is showing the cell splitting. You can see that smaller cells are coexisting within bigger cells. Here the base stations are placed at the corners of the cells and the area served by base station A is assumed to be saturated with traffic. New base stations are needed in the region to increase the number of channels in the area. Base station A has been surrounded by 6 new microcell base stations. These smaller cells added preserves the frequency reuse plan of the system. Example, the microcell base station labeled G is placed half the way between two larger stations utilizing the same channel set G. The radius of each new microcell is half that of the original cell. The power received at all cell boundaries is proportional to PT1 times R to the power of minus n. Power received at a new cell boundary is proportional to PT2 times R by 2 to the power of minus n. PT1 and PT2 are the transmit powers of the larger and smaller cell base stations respectively, and n is the path loss exponent. Take n equal to 4 and set the receive powers equal to each other, then PT2 equal to PT1 on 16. That is, the transmit power must be reduced by 12 dB for the coverage with microcells while maintaining the signal to interference requirement. If larger transmit power is used, smaller cells will have co-channel interference. If smaller transmit power is used in larger cells, some parts of the larger cells will be left unserved. Channels in the whole cell must be broken down into two channel groups, one for the smaller cell reuse requirements and the other for the larger cell reuse. The larger cell is usually dedicated to high-speed traffic so that handoffs occur less frequently. By decreasing the cell radius r and keeping the co-channel reuse ratio d by r unchanged, cell splitting increases the number of channels per unit area. Sectoring increases the capacity, keeping the cell radius unchanged and decreasing the d by r ratio. Sectoring increases SIR so that the cluster size can be reduced. First, SIR is improved using directional antennas. Then capacity is increased by reducing the number of cells in a cluster. The co-channel interference can be decreased by replacing a single omnidirectional antenna at the base station by several directional antennas, each radiating within a specified sector. By using directional antennas, a given cell will receive and transmit with only a fraction of the available co-channel cells. The technique for decreasing co-channel interference and thus increasing system capacity by using directional antennas is called as sectoring. The factor by which the co-channel interference is reduced depends on the amount of sectoring used. A cell is normally partitioned into 3 120-degree sectors or 660-degree sectors. The Channels used in a particular cell are broken down into sectored groups and are used within a particular cell. 120 sectoring and 60-degree sectoring are shown in the figure. Assuming 7-cell reuse, for the case of 120-degree sectors, the number of interferers in the first pair is reduced from 6 to 2. Consider the interference experienced by a mobile located in the rightmost sector in the center cell labeled 5. There are 3 co-channel cell sectors labeled 5 to the right of the center cell and 3 to the left. Out of the 6 co-channel cells, only 2 cells have sectors radiating into the center cell. Mobile in the center cell will experience interference on the forward link from only these 2 sectors. The resulting S by I ratio can be found out as 24.2 dB, which is a significant improvement over the omnidirectional case 17 dB. Because of the reduction in interference, cluster size n can be reduced. Disadvantage: increased number of antennas at every base station and a decrease in the trunking efficiency due to channel sectoring at the base station. Sectoring reduces the coverage area of a group of channels. The number of handoffs increases. Many base stations support handoff from sector to sector within the same cell without intervention from the MSC. So handoff problem is not a major concern. Repeaters for range extension. A wireless operator provides dedicated coverage for hard-to-reach areas like within buildings, tunnels, etc. Radio retransmitters known as the repeaters are used to provide range extension capabilities. Repeaters are bidirectional in nature, simultaneously send signals to and receive signals from a serving base station. On receiving the signals from a base station, the repeater amplifies and re-radiates the base station signals to the specific coverage region. So repeaters do not add capacity to the system. Microcell zone concept. More number of handoffs required in sectoring results in an increased load on the cellular system. A solution to this problem is the microcell concept, which is shown for n equal to 7. Each of the 3 zone sites are connected to a single base station and share the same radio equipment. The zones are connected by coaxial cable, fiber optic cable, or a microwave link to the base station. Multiple zones and a single base station make up a cell. As a mobile travels within the cell, it is served by the zone with the strongest signal. This is superior to sectoring since antennas are placed at the outer edges of the cell and any base station channel can be assigned to any zone by the base station. As a mobile travels from one zone to another within the cell, it retains the same channel. This handoff is not required at the MSC when the mobile travels between zones within the cell. The base station simply switches the channel to a different zone site. A given channel is active only in the particular zone in which the mobile is traveling, and hence the base station radiation is localized and interference is reduced. The channels are distributed in time and space by all 3 zones and are also reused in co-channel cells in the normal fashion. Advantage: the co-channel interference is reduced since a large central base station is replaced by several raw power zone transmitters. Decreased co-channel interference improves the signal quality and leads to an increase in capacity without degradation in trunking efficiency. A system with n equal to 7, that is D by R ratio equal to 4.6, can achieve S by I of 18 dB required for satisfactory performance. Since transmission at any instant is confined to a particular zone, DZ on RSET of 4.6 can achieve this. DZ is the minimum distance between active co-channel zones and RSET is the zone radius. The distances D, DZ, R and RSET are shown in the figure. Each individual hexagon represents a zone, while each group of 3 hexagons represents a cell. The zone radius is equal to 1 hexagon radius. The capacity of the zone microcell system is directly related to the distance between co-channel cells and not zones. This distance is represented as D. For DZ on RZ equal to 4.6, the value of D by R equal to 3. From the geometry, where R is the radius of the cell, d by r equal to 3 corresponds to a cluster size of n equal to 3. The reduction in the cluster size from n equal to 7 to n equal to 3 amounts to a 2.33 times increase in capacity over a conventional 7-cell system using omnidirectional antennas. Hence, for S on I requirement of 18 dB, this system provides a significant increase in capacity. The exact worst case S by I of the SON microcell system can be estimated to be 20 dB. No loss in trunking efficiency is experienced. The references are also given. Thank you.